The purpose of this experiment is tracking the motion of an object that is falling and that can feel air resistance. Comparing the experimental data with theoretical data from two computational models, one considering drag and the other ignoring it, by observing position and velocity plots, and discussing how close the real-life example is to the theoretical models and identifying sources of error. Some of the principles and models involved in this experiment are Newton's second law, the general kinematics equation, and the equations of motion, as well as the drag force formula, the force and acceleration of gravity near the surface of Earth, and the concept of jerk. When comparing the position versus time plots, it was observed that the experimental data and the drag model curves have a similar shape, some curvature when t is close to zero but more linear when not. The freefall model curve quickly diverges from both those curves and its curvature is constant. Thus, it was found that the motion of a falling object can be modeled more accurately by considering air resistance. This means that the object's acceleration when falling in air is not constant. To analyze the motion of a falling body that is being affected by drag, we draw free body diagrams to help our understanding. At t equals 0, v equals 0 meters per second. Since the drag force is proportional to velocity squared, the force of drag is 0 newtons, hence the net force equals the weight. Then, the acceleration equals the acceleration of gravity. At some time during the fall, the velocity does not equal 0, hence the net force will be the sum of the weight and the drag force. Then, the acceleration won't equal the acceleration of gravity. There will be a change of acceleration. I assume that the rate at which acceleration changes is constant. Then to predict the position, I use a more general expression for the position, where n is the order of the highest non-zero derivative of position. The general kinematics equation cannot accurately model this situation as it does not consider higher derivatives of the position. As jerk is the highest non-zero derivative, n equals 3, and considering y coordinates, we obtain the following equation, where j sub y is the y coordinate of jerk. Consequently, a cubic fitting curve should be used to model the vertical position. As drag is proportional to the speed squared, at some point the magnitude of drag force will equal that of the force of gravity, hence the net force will equal 0 newtons. And according to Newton's first law, the object should remain in constant velocity motion. The speed at which the weight equals the drag is the terminal speed. The object was set at an initial height of 1.8 meters, and markers were used to measure distance. The distance between markers was 0.02 meters. The system is the falling object, which in this case was a paper helicopter, and the surroundings was everything else. The main elements from the surroundings executing force on the paper helicopter were the earth and the air. The paper helicopter was dropped from the top of the covert without applying any forces. The only force acting on the system at t equals 0 is the weight. The position at each frame was annotated using tracker, and the position of the paper helicopter was plotted against time using Logger Pro. The data points are fitted with a cubic curve, and the drag constant can be found by observing the value of velocity for which there seems to be a horizontal asymptote. Thus, the drag constant was estimated to be equal to 0.00236 kilograms per meter. For the model, first we define the object's mass and drag constant, and we set up time steps for iterations. We also define the acceleration of gravity and define the coordinate system and the positive direction of y. Now we set up a function for the net force as the sum of the weight and the drag force. In the freefall model, the term for the drag force is omitted. In each iteration, the computer takes the velocity and updates it using the net force. Then both the position of the object and the net force, in the case where drag is considered, are updated. This process is iterated until the time reaches a defined value. These are the position versus time plots obtained using the model. Comparing the three curves, we can see that the experimental data and the model with drag curves seems to be pretty similar. We can see that both have a slight curvature when t is near 0, but as it grows, the curve becomes more straight. This means that the second derivative of the curves is close to 0, which means there's no acceleration. The object has thus reached the terminal velocity. However, the freefall model quickly diverges from both of them, and it seems to have a non-zero second derivative, as it is always curved. The drag constant was obtained under the assumption that jerk is constant, which in the real life is not. This can also be the cause for why the experimental data curve is shifted with respect to the model data. Also, the camera angle may have distorted the position data points, slightly altering the results of the experiment, and the tip of the paper helicopter was small, as it was difficult to manually track, which could have led to some random error. The launch may not have been perfect, and a small force could have been applied to the object. Which models predict the terminal velocity? Now we plot the velocity versus time curves from the models, and we compare them to the real experimental data. Again, the experimental data and the model with drag follow a similar shape, whilst the freefall model quickly diverges from both curves and is completely straight. However, we can see that both the experimental data and the model with drag approach some velocity value when time grows, which means that they are getting to terminal velocity. So both of those, both the model with drag and experimental data predict the terminal velocity, whilst freefall model doesn't. As the force is proportional to v squared, if the object is thrown downwards, the initial speed will be non-zero. Thus, the object will experiment at drag force at time equals 0. However, the drag force will still have to be equal to the weight for the object to reach terminal velocity. In this situation, the terminal speed will be the same. The only difference is that the object will reach it faster. In conclusion, the object's position can be reasonably compared to a model of a falling object being affected by a force proportional to the speed squared. This means that falling objects in the air experience a drag force and eventually reach its terminal speed when force net equals force drag. This means that falling objects in air experiment a drag force and eventually reach a terminal speed when the weight equals the drag. In the y versus t graph, the point at which the object reaches terminal can be interpreted considering that the second derivative of position is 0, so the graph becomes linear.